A couple notes. So there were people in my office hours and I kept getting the same couple questions, so I thought I'd clarify a few points from your homework really quick, since you still have a few hours. First of all, negative numbers exist. So like when you bound to error, you need to take absolute values and you need to make sure that like when you remove absolute values or when you push them into fractions and things that you're doing this in a way that makes sense for positive and negative numbers. I know this sounds stupid, but I literally had at least 9 people come to my office hours, all with the same couple of things. By the way, is the camera on?
Yeah.
Oh, okay, cool. A couple other things, let's see here. When I ask you to bound the error of an expression, you should bound the error and not bound some other thing and then try to plug it into the error, because you're probably going to make a mistake. In particular, for one of these problems, right, I asked you to compute the error of computing n times x by just adding x plus x plus x plus x plus x. Hopefully this is familiar. Yeah, so a lot of you guys bounded this number and then tried to plug it into another bound. If you do that, you need to be very careful how you plug that into your bound of the error. This is not the error. This is the sum. This is some other number. And saying that this number is like less than or equal to like 7n or something is like, it might be a valid bound, but it's not an interesting one. We're interested in bounding the error of a computation. Yes?
And when you say the error, you mean the relative error?
The relative error, yeah. So basically all this is to say that be careful when you put these inequalities, be careful which way they face and that they work for positive and negative numbers. And then the third announcement is I had about, I think 6 people today kind of show up in my office with questions. This is okay, and I'm happy to help you not during my office hours, but I would like you to send me an email ahead of time and schedule some time. I have to do some research, and it's a little disruptive for me to have this. Cool? All right. So without further ado, sorry, are there any questions about homework, procedural stuff, last lecture, someone? Okay, your next homework is posted on the course website. As usual, those who start early will be rewarded both with less stress next Monday and with all the typos that are probably in my problem set. Yeah, okay. So we're going to finish up from last lecture and then get started on the next topic. We're a little bit behind the schedule that's on the course webpage, but that's okay. I built in some wiggle room toward the end of the course with some topics that shouldn't take as much time as I observed. So anyway, if you'll recall from our last lecture, we were talking about linear systems of equations that have special structure that we can take advantage of when we're solving. Right? In particular, we discussed this case where if we can check that a matrix is positive, definite, and symmetric, then we have this whole other way of factoring the matrix and solving the system, right? This Cholesky factorization that we can't use for just a generic matrix, right? So in general, I think a good theme to get out of this week is that the more you know about a numerical problem, the better off you'll be designing algorithms to solve it. And I think this is kind of a reasonable fact, but one that you should keep in mind. So we already talked about symmetric positive definite systems. Another example that shows up so many times in numerical analysis is sparsity. And we're going to return to this in a couple weeks, but I thought I'd mention it now. Now, one problem that shows up in my research field is this idea of harmonic parameterization. How many people have seen this in a computer graphics class? Gavin, I know you have because you took my class in the spring. Okay, so right, so harmonic parameterization, the idea is, let's say that I have a 3D model of the cow. It's constructed out of a bunch of triangles, and I want to texture the cow. So normally, in a computer graphics system, we store a texture in like a JPEG image, right? So like here's texture.jpg, right? But then we also, I'm not even going to try to draw a cow, but we will approximate the cow with a triangulated square. And, sorry, and here's the 3D shape that's sitting in space somewhere, right? And the idea is that we come up with a mapping from this 3D cow sitting in 3 space down into the plane, right? It might warp the cow a little bit, such as light. Right? And then when we want to render the cow in 3D, we're going to look up the texture in this 2D object, because we're good at storing images in 2D. Right? So the problem of texturing kind of makes sense. And so something that we solve in geometry processing a lot is how do you come up with this map from the 3D object into the texture plane? And you want to do so in a nice non-distorting way, right? You'd like sort of you know, an equal number of pixels to correspond to an equal amount of area on this guy, roughly. So one very common algorithm for this, sort of the most classical approach, and the one that's used in practice the most today, is this idea of harmonic parameterization. So in harmonic parameterization, at least the sort of simplified version that we'll talk about, what we're going to do is we're going to say, okay, let's say that I'm an interior vertex V, right? So here's V. And he's not on the boundary of the count, right? So he's got lots of neighbors in this triangulation. Then one sort of property of a triangulation that would make it a very nice one would be, let's say that we're going to number off his neighbors, like W1, W2, and so on, right? We'd like for V to be at the centroid of his neighbors. Right? So for example here, this V is approximately average at least 4 points, and somehow this gives a nice non-distorted triangulation, right? Because every time you have a vertex, somehow he wants to be equidistant from all of his neighbors. This is just one sort of heuristic criterion. It turns out that it corresponds to some nice differential geometry, but we don't have time for that today. So, right, so one very easy linear system of equations that you could write down for harmonic parameterization is to enforce this thing exactly at every vertex. Right, so let's say that our unknowns here are like a V1, V2, all the way to Vn, right? The positions of all of the different vertices here, right? Then you could think of an operator that takes a vertex, that takes the neighbors of a vertex and averages their positions, right? This is obviously a linear operator if you think about it, right? You're just adding a bunch of things together. We'll call that operator A, right? And then we want that thing to look like the vertex in the center, right? So we want to subtract off the actual guy in the middle, and what do we expect to get out of this process? 0, right? What did I do? I averaged my neighbors, and then I subtracted my position, but I'd like these two things to be the same, so I can do that. Right? This is a linear system of equations. It turns out it's underdetermined. One way to make it not underdetermined is along the boundary of your surface, you specify the positions. You can see here, along the boundary, like the neck of the cow, they just place the vertices of the neck of the cow around a circle. Easy thing to do. And then it turns out that this system of equations is completely specified, invertible, well-conditioned, and so on. But it also has one really interesting property that we haven't talked about in CS205A yet, which is that it's sparse, right? Now in particular, what do we know about the row of this system of equations corresponding to V? Like how many non-zeros are there? Well, I can tell you. There's 1, 2, 3, 4, 5 non-zeros in that row. Right? So let's say that my mesh has 10 million vertices. Right? So how big is this system of equations? It's 10 million by 10 million. Right? That's an awfully big system of equations. But how many numbers in that matrix are actually non-zero? Well, on the order of 5 times 10 million. Right? The rest of them are just a bunch of zeros because I don't need to average this guy with like a bunch of vertices on the other side of the mesh. Right? I'm just dealing in this little local neighborhood. And this is a pattern that shows up a lot, especially in computer graphics, when you tend to have these nice smoothing operators where you're averaging with your neighbors and so on. So the first question is, if this matrix is n by n, right? So how we know how to store matrices so far is just by like an order n squared thing, right? Just a table of all the different numbers in the matrix. But there's really no reason to do that here, right? If we only really have like 5 times n numbers in this matrix, then we're storing a lot of numbers that are all 0. So there are a couple choices we can think about for different ways to store sparse matrices. And really, what we want is order n storage if we have order n non-zeros. I think that's a reasonable theme. And so there are lots of things you could do. For example, you could just keep a list of the non-zero elements in your matrix. Easy enough. Obviously, if you want to search for elements in your matrix or check if something is non-zero, this is not the best data structure. Another option might be for each row, you store sort of a dictionary that only holds the non-zeros in that row. Right? There's if you look at the MATLAB documentation, you'll see they have a really bizarre representation of sparse matrices that sort of orders the non-zero things in a particular way, row by row. And this is sort of a compromise between these two things, but I don't think it's worth spending a whole lot of time. But anyway, all this is to say that when you have a matrix that's sparse, you shouldn't be storing an n squared thing. You're wasting a lot of time. But of course, in the end, if we're doing Gaussian elimination, we have to go back and reconsider our algorithms and make sure that we don't violate the sparsity assumption while we're inverting the matrix, right? So in particular, let's say that I did Gaussian elimination on this guy in the left, right? Obviously, he's a very sparse matrix. Well, I should have, actually, this first column should be x, 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 x down there. So it's like an arrow shape. Sorry. Is that cool? I mean, typo. Right. So what happens after the first step of forward substitution? I'm going to take that first row, and I'm going to add multiples of that first row to all the other rows. Right? Well, what did I do? I annihilated all of the zeros in this matrix, potentially. So I went from an order n size thing to an order n squared size thing, and my algorithm might explode. Right? In particular, in computer graphics, a lot of times you can only afford storage on the order of the number of vertices in your mesh, for example. The number of vertices squared is just too big. And so you have to be very careful about this phenomenon called fill that happens especially in algorithms that are derived from Gaussian elimination. So how do you avoid fill? Well, the most common strategy is actually to just permute rows and columns in such a way that when you do these forward and backward substitutions, a lot of times there's just already a zero there. Right? So that means that during your Gaussian elimination now, you're not just pivoting to find big numbers to divide by, but you're also pivoting to get zeros in places that you like. Right? Unfortunately, this can be NP-complete to minimize the fill, the fill of, for example, Cholesky decomposition exactly, but there are lots of heuristics that we won't be able to get into in this class because they're quite difficult to think about. Another strategy that is easier to think about is to avoid Gaussian elimination altogether, and that's something we'll come back to in a couple of weeks. But anyway, this is just to say that when you look at your matrix system, I want to warn you now, because I know there are people that are taking this class that are like immediately applying this to their research, which is cool. But if you have the sparse matrix, you shouldn't be using what we covered in the first couple of weeks of 205. That's not to say it's not useful. There are plenty of matrices that are dense. But there's a completely different set of machinery that is useful for these types of problems. By the way, a piece of software that's really fun to play with is called Sweet Sparse by a gentleman in Florida. And this is state-of-the-art for applying Gaussian elimination to sparse matrices. And it's all about minimizing the number of non-zeros that happen when you do these forward and backward substitution steps. And you can, if you look at the documentation, you'll see it's some really complicated stuff.
Is it order n because you're going down, and then n squared because you're doing n rows?
So it's not, we're not talking about timing. We're talking about the amount of storage. So think about like if each row only has 5 non-zeros, right? Then you have 5 times the number of rows, numbers that you really need to store in this matrix, right?
Oh, I see. Okay.
But the matrix is of size row squared, right? So somehow you're storing a lot of numbers that are all 0. Yeah. So that's the idea of a sparse matrix. And when we come back and talk about machinery like, for example, conjugate gradients, then this is going to come into play because the conjugate gradients algorithm, all it cares about is that you can apply your matrix. You can multiply it by things. And you can multiply sparse matrices just as easily as you can multiply dense ones. Cool. There are other types of special structure that I thought I'd mention, and these are all easily Googleable, and maybe will show up on your homeworks or exams or whatever, but really aren't worth a whole lot of class time because they're rather specific. Some other kind of families of matrices that you might see in the wild include things like banded matrices. These ones say there's some sort of thick diagonal structure to your matrix, and everything is 0 except for that thick diagonal. A particular type of matrix that's very common in this sense is the tridiagonal matrix, which is what I showed here. And in fact, it's pretty easy to show that Gaussian elimination can be carried out on tridiagonal things very efficiently. It's a very slick algorithm for that. Sometimes you have cyclic matrices. So for example, here you see the first row is A, B, C, D, and then all the rows underneath that are just that, rotated over by 1. This shows up a lot of times when you're solving equations with periodic boundary conditions. Okay. And so on. So basically, all we're going to talk about in 205A, since we don't have time to cover each of these in detail, is that when you look at your matrix, you should be very critical. Right? You should think about all of the special structure that you can get out of it before you apply your solver, especially if you're worried about speed, stability, conditioning, and so on. Okay. Now, if we return to that case that I talked about before, right? I got all excited about Cholesky factorization because we started by motivating our whole discussion with this least squares problem, right? And we noticed that this matrix A transpose A is really the equation, the matrix that you want to solve when you want to solve this least squares AX sort of equals B, right? So this thing now has too many rows to make this an exact equal sign. So remember our story from last time is that in fact, we're going to solve A transpose AX equals A transpose B. And we decided this was the KKT, or rather the Lagrange multiplier conditions for minimizing the difference between these with respect to the two. Yeah? Nods? Yeah? This is familiar? Cool. But there's a problem. Now remember, we talked about the condition number. See, none of this stuff has been a mistake so far. We discussed the condition number of a matrix, and one reasonable question to ask is, what is the conditioning of A transpose A relative to just A? Yeah? So we can actually just do this calculation, right? Because we know the condition number of A transpose A is what? It's the norm of A transpose A times the norm of the inverse of A transpose A. Yeah? And now you'll prove on your homework that for certain matrix norms, in fact for most matrix norms, it's true that the matrix norm of a product is approximately equal to the product of the matrix norms, certainly bounded above, and in fact, oftentimes that's pretty close to an equal sign. But now if I reshuffle terms a little bit here, in the third row here, what do we see? Well, this is just the condition number of A squared. Yeah? So remember what the condition number tells you, right? If A is a poorly conditioned matrix, right, like we're going to have a lot of trouble solving AX equals B, then the condition number is big. Yeah? And what's a big number squared?
Bigger.
Even bigger, right? So if we want to solve one of these least squares problems, we're a little bit hosed, because now we have this humongously difficult matrix to invert. We're going to be dividing by very small numbers and doing all kinds of numerically very poorly advised operations in the process. And so we need to fix this problem. And this is our motivation for the next part of CS205, which we'll start today and probably not get to the end of. Okay. Yes. Every time. Okay, and with that, we begin our discussion of the QR factorization. Alright, so here's our problem. Written in even bigger fonts so that you acknowledge how important this problem is. And let's begin to solve it. So first of all, one question you might ask is say, okay, we're trying to design algorithms that avoid this kind of stuff. When isn't this condition number issue a problem? Well, we know that the condition number of the identity matrix is 1 for almost any matrix number. In fact, I think for all matrix norms. Yeah. So certainly, if we can manage to solve the identity times x equals b, can somebody provide me with the solution to that equation? Yeah, it's not a hard equation. B, yeah, x equals b. Yeah. In fact, the equation itself is x equals b, right? But here's the thing. Remember, when we want to solve this least squares problem, we're not actually solving AX equals B, we're solving A transpose AX equals A transpose B. And we could get really lucky, right? And even though A might be God knows what matrix, this matrix A transpose A might be the identity. And if this is the case, in this particular, very lucky, like God knows why this might happen situation, the least squares problem is very easy to solve, and the condition number thing I was just complaining about isn't an issue. Hopefully you all agree with me. But of course, the question you should be asking is like, okay, well, like, great. So if I'm really lucky in this measure zero set of matrices, maybe I'll be able to invert and life is good. But chances are, when I'm just collecting data in the wild, there's no reason why I should get the identity when I just take my matrix, flip it on its side, and multiply it by itself, right? So what A transpose A is doing. So let's think about what's going on. By the way, any matrix that satisfies matrix transpose times itself equals the identity, I'm going to try and call Q in this lecture to disambiguate. And what is Q transpose Q? Well, from your zero-width homework now, you've already done this calculation, hopefully, right? When you take Q transpose, if the columns of Q are just Q1 to Qn, right? Then Q transpose, now the rows of Q transpose with the columns flipped on their sides, yeah? And when you do this, you get the dot product between all the different columns of Q. Right? Remember that this thing is what we want to have equal the identity matrix. So in particular, we know that the diagonal of this guy is going to equal 1, and everything else equals 0. Yeah? So what does this mean? That means that each of the columns has norm 1, right? Remember, this is the dot product of Qn and itself. Right? So this is just the norm of Qn. So we know the norm of Qn is 1, and we know that like Qn dot Q2, for example, is 0. So in other words, all of the vectors are mutually orthogonal, and they all have unit length. Yeah? Hopefully this story should start to sound familiar from Math 51 or equivalent prerequisite knowledge. Yeah? So again, when is Q transpose Q equal to the identity? Well, it's when the dot product between two columns is 1, when you have the same column, and it's 0 otherwise. Yeah? And what does that tell us about life? Well, we're going to call this matrix an orthonormal, or an orthogonal matrix, and we'll call these a set of vectors that satisfies this property, we'll call them orthonormal. Right? So again, a set of vectors is orthonormal if they all have norm 1 and the dot products are all 0. Yeah? And a matrix that looks like this is called an orthogonal matrix. So now we have a special name for this thing that we're looking for. We haven't shown that we have any reason to find it, but we're going to give it a name. So let's go into a little bit more depth. Okay. So first of all, what kind of properties does this matrix Q have? Well, we call Q, as a differential geometer, I have to call Q an isometry. I guess this shows up in linear algebra sometimes. But what do I mean by that? I mean that Q preserves angles and lengths. In particular, what is the norm of Q times vector x?
The norm of x.
It's the norm of x, and it's very easy to prove that using, again, yet again, the same, right? You know how your 0th homework made you do these calculations 100 times? There's a reason, right? So remember that this is the same as the dot product of qx with itself, and that's the same thing as this guy transpose times itself, yeah? What is Q transpose times Q?
Identity.
The identity. Yeah, so in the end you get x transpose x, and that's equal to the norm of x squared. Similarly, qx dot qy, well, exactly the same thing happens, but now you get, for example, a y here, maybe, and you get the dot product between x and y, right? So Q sort of doesn't do anything interesting to the geometry of Rn, right? It's just, because you can think of the dot product as sort of one way of thinking about angles, right? And then norm as a way to think about distances and lengths, but somehow Q doesn't do anything to either one, yeah? So this is a very special type of matrix. It's an isometry of Rn, and we're kind of looking for it. So now let's return to our favorite least squares problem. And we're going to have yet another interpretation of what it means. Now, in particular, remember our least squares problem? You can put a square up there if you like. Right? You'd like to minimize the norm of ax minus b. Right? So what is ax? Well, remember that when you take a matrix and you multiply it by a vector, you're effectively just combining, linearly combining the columns of that matrix. Right? So ax is just something in the span of the columns of A. Right? And then what do we want to do? We want to find the thing in the span of columns of A that's as close as possible to B. That make sense? So in other words, we want to project B onto the column space of A. And this is going to be the interpretation that's going to get us to a much more numerically stable approach to least squares problems. And to get there, we're going to make one observation about life. This is where I think my discussion differs a little bit from the Heath textbook, but such is life. So, here's the observation we're going to make. For any A in Rn by n, so just a generic matrix A, and any invertible matrix B, the column space of A is equal to the column space of AB. Let's prove this fact really quick. So, we'll say, claim for all A in Rn by n, and invertible B in R, what did I say, n by n. And we have column space of A is equal to column space of A. Now why is this fact true? I have my notes in my bag, but hopefully we won't need them. So let's take any vector in the column space of A. Right? So let's suppose V is in the column space of A. Right? Well, by definition of matrix multiplication, that means that there exists some x so that Ax equals V. Right? Because remember what matrix multiplication does? It just linearly combines the columns of A. Right? Well, what does this mean? Well, another way that I could write this, right, would be A times B times B inverse x equals B, right? And now if I group this like that, you can see that V is in the column space of AB. See what I did there? It's tricky, because this is just some other matrix, or some other vector in column Y. right? So AB times Y equals B. And by basically assuming an identical argument in the reverse direction, you can show that this is an inclusion in both directions. Yeah? Everybody believe this fact? No, there are literally 5 people sleeping in this room right now. Now they're awake. Okay. Right. So in other words, if you do invertible column operations, remember that when you post multiply, you are doing column operations on this matrix A. They don't affect the column space. So if we're trying to solve this least squares problem where we project a vector onto the column space of A, we can do whatever we want on the right-hand side of A without messing with our problem. Yeah? Now we're starting to figure out how we might be able to get to the space of orthogonal matrices. In particular, we have a new strategy, which is we're going to do column operations on A. Remember in Gaussian elimination we do row operations. Now we're going to do column operations on A, because by our lemma here we know that we haven't screwed up the column space. And remember that least squares is all about projecting onto the column space. I'll get to you in a second. We're going to do column operations on A until it looks orthogonal. And then we're going to solve the least squares problem with the orthogonal matrix because we know that's an easy thing to do. Yeah? Catherine?
Oh yeah, so what does column operations mean versus like row operations?
So a row operation is like left multiplying your matrix by something. So for example, permuting 2 rows is a row operation, whereas permuting 2 columns is a column operation. So in general, you think of row operations as left multiplies on your matrix and column operations as right multiplies. Yeah. Any other questions? Cool. All right. And in the end, I'm going to jump to the end of the story and then we're going to fill in all the steps in between. We'll obtain a factorization A equals QR now, where Q is going to be orthogonal. Remember, that's what we wanted. And R is going to be something easy to solve. Remember, this is a pattern that we saw in LU factorization too, right? We started with the matrix A, and we started multiplying him on the left by a bunch of elimination things until we got a matrix that we liked. Now we're going to take A, and we're going to start multiplying him on the right by a bunch of elimination things until we get Q, right? Because that's our job, is to find an orthogonal matrix. Right? So here's Q, and then you can think of this thing as R inverse, right? This is a useful factorization so long as Q is orthogonal and R is something easy that we know how to deal with. Yeah? So that's going to be our goal for today. And in particular, why is this easy? Well, let's say I wanted to solve that least squares problem. I'm going to erase this, if that's okay. Yep. Okay, so let's say we want to solve A transpose AX equals A transpose B, right? Our favorite system of equations. But what is this thing? For this guy, you remember A is equal to QR, so this is equal to R transpose Q R. X equals R transpose Q B. Yeah, I did that right? I did. Now, great. What is this thing? This is the identity, right? So this is the same as R transpose Rx equals R transpose Q transpose B. Yeah? And in particular, for now, we're going to kind of assume we can remove these R's. This is not a completely rigorous step, but ignoring that for now, we see an R on both sides, and we can remove him, and we'll get Rx equals Q transpose B, and we'll have to go back and justify that we can do that. But in the end, this system of equations is very easy to solve. Right? In fact, we'll find that we can do a factorization for which this R is upper triangular. Right? So this is just an upper triangular system of equations. Right? I take B, and the first thing I do is I pre-multiply by Q transpose, and then I just have to solve this upper triangular thing. So life is good. All right, so let's figure out some details. First, you'll notice that we're sort of moving in parallel to just a standard linear algebra class and filling in the computational details as we go along. And I'd say the next thing you learn about in linear algebra after you cover sort of the basics of Gaussian elimination is this idea of a projection, right? So like we project one vector onto another and so on. Now to me, right, since I have to write all things variationally, it's just, my life as a continuous mathematician, I like to think of the idea of a projection both as a geometric object and as an energy minimization. So let's say that I want to project B onto A, right? So geometrically, right, I have a vector A, I have another vector b, right? And I kind of want to find the point parallel to A that is closest to B. This is hopefully a picture you've seen before. Right? In fact, probably the picture you've seen before does that, but we're going to prove that in a minute. Right? So we'll call this point here, it'll be the projection onto A of B. By the way, I have a propensity to accidentally flip these two guys. If I do that, you should keep me honest. Okay. So hopefully our goal makes sense. We want to project stuff. Yeah? So how are we going to do that? Well, there's a really slick way to derive projections given the heavy hammer of these squares that we've already derived. So in the end, you can think of our optimization, right? You can define this energy, E of C, right? And he's just the norm of C times A minus B squared, right? And obviously we want this thing to be as small as possible, right? Because then this multiple C times A is going to be the thing parallel to A, and we want it to be as close to B as we can, so we just take the difference and square it. Hopefully you guys see how these two problems are sort of the same. Well, this is a least squares problem, and we know how to solve least squares problem. In particular, I'm going to move the C to the other side of A. It seems like a stupid thing to do, but the reason that I do that is you can think of B as an n by 1 matrix, A as an n by 1 matrix, yeah? C is a 1 by 1 vector, right? So what are the normal equations of this least squares thing? Well, remember it's A transpose A, X equals A transpose B. And in this case, what do we get? We get vector A transpose vector A times C equals vector A transpose B. Isn't that slick? Right? Normally you have to do calculus and all that, but here we already did the calculus. So now we've in particular, this tells us what about C, assuming I did it right. Remember, well, these numbers are just 1 by 1 matrices, right? These are scalars, right? So I can divide, and division is okay. And in particular, I get that C is equal to A dot B over A dot A. This is probably a formula you've seen before, and a particularly slick proof because we have this sledgehammer of these squares that we've already gone through last week. Yeah? All right. So what does this tell us? Again, here's our expression for C, and if we plug that back into our formula for projection, right? Remember, this is our projection onto A of B. Well, it's just C times A. Now we get this expression here, which is probably very familiar to you guys. Yeah? How many of you guys have seen this before? Yeah. Also, who just fell upstairs? What was that? This classroom is full of surprises. Okay. So let's think about some properties of projection. Well, first of all, obviously the projection of B onto A is parallel to A, kind of by construction. And now, what if I take B and I subtract off the component that's parallel to A? Right? So you can think of decomposing B into the sum of two things, right? This guy, who's the projection, and this other guy, which is the thing that's left after you project. Right? That's what I did here. If I take the dot product with A, you get 0. Does anybody need me to go through this calculation, or can you believe me for now? And it's as simple as plugging in the formula we had before, and everything just cancels. So in the end, what does this mean? Well, this means that the projection is parallel to A, and the remainder, B minus his projection, is perpendicular to A. Right? So we've now decomposed this guy into two very convenient pieces. By the way, I think one of your homework problems this week makes use of this decomposition for a very slick answer. Or I might have removed it, I forget.